Okay, this is the first lecture on the continuous groups, but we're going to couch it, the terminology, in terms of the harmonic oscillator. First, the harmonic oscillator, one-dimensional. That's what we'll talk about today. The unitary group of one dimension, which most people consider too trivial to even discuss. It's far from trivial. It's all of the theory of a harmonic oscillator, which we'll go over today. The idea of the raising operators, the lowering operators. Those are things that you find in angular momentum theory. Everybody knows about that. But many people aren't familiar with is the fact that these are the operators that make those operators, and then the theory becomes simpler. But we're going to be talking about not just the raising and lowering operators and the number operators, but also later on operators that shove and kick. That is, operators that do a boost or a translation. And it'll be an exponential of some generators. So this is where you get to see the simplest possible Lie group and algebra, just in the context of U1. The next lecture, U2, a little bit of talk about U3, and so on. By that time you'll begin to get a feeling for really what it is that unitary group theory provides us, and that is a whole field of oscillators. In how many dimensions? Well, a molecule has 3 dimensions for every atom. If you're going to just do classical oscillator theory of vibrations for an atom, that's all you would talk about. And then out of the states of the quantum oscillator would come your quantum theory for a molecule that only vibrated. Well, molecules vibrate and rotate, and their electrons get excited. That's all stuff that makes the problem really hard. We'll be able to talk a little bit about the rotations after we get done with this one. But in any case, I'm going to be giving to you the best presentation I can think of for the creation-destruction algebra that every oscillator theory has. And it will be, well, I could say creationism. We're in Arkansas and have to worry about creation science, right? Well, here's where it starts. And the vacuum state and the first excited state will be things that we create using a creation operator. And then some of the matrix calculations you have to do for field theory, normal ordering of these operators, that's sort of the hard algebra part of the oscillator theory. Once we get that done, other things follow fairly easily. So we'll see that the number operator, which is A dagger A, is the Hamiltonian operator. We'll also see how expectation values are really easy to calculate once you get this sort of algebra out of the way. And then finally, the translation operators and the boost operators. How do you make what are called a coherent state, or a coherent state that's been diddled with a little bit is called a squeezed state. We'll look at all of that. Now the next lecture will take up this, but I put it on here anyway just to get ready for U2. Okay, so let's go and do the basic idea of solving the harmonic oscillator in a quantum mechanical way. So that's the question. How do you convert a classical harmonic oscillator Hamiltonian, our good old 1/2m p squared plus 1/2 a spring constant k, that's m omega squared, multiplying the spatial variable x squared. Okay. Well, the answer, sort of a joke I make out of this, is that you rewrite the classical Hamiltonian with a thick pen. Right? There it is. You take the p, which you want to be an operator, and replace it with a symbol that indicates an operator. While you're doing it, all quantum mechanics from classical mechanics sort of does this nowadays. And so there you are, but you don't know anything yet. However, the idea that momentum is related by de Broglie's relation is important. We'll get to that a little bit later. Now,
the question is, okay, so you've written with a thick pen. How do you solve this Hamiltonian for its eigensolutions? And my joke is, you rewrite this thing with a thicker pen. And this particular way of writing it makes it sort of obvious what you have to do in order to solve this thing. So I replace the slightly thick x with a thicker x, and the slightly thick p with a thicker p that has these scale factors buried. The idea, you see, is there is some symmetry here between position and momentum. This Hamiltonian, when scaled properly, is totally symmetric to the interchange of coordinate with momentum. That's the kind of symmetry we haven't mentioned at all. All of our symmetry so far has been to do with spatial variables. But really, in phase space, you've got to consider that symmetry too. And that's what you've got, is a Hamiltonian that says, hey, you want to change position and momentum? Be my guest. That's really amazing. Now, because of that symmetry, we can easily solve this particular problem analytically and beautifully. Okay, so I say, yeah, but how do you really solve a Hamiltonian, whether you've done this or not? Answer, factor it. Factor p squared plus x squared. Okay? P squared plus x squared is x minus ip, x plus ip. And that might be all there would be to it if it were not for the fact that I need to add, see, I have a symmetry here, I need to add another term that makes it symmetric. And the reason for that is, as we recall, is that either the thick x and p or the slightly thick x and p do not quite commute. Okay? Now let's look at that before we go any further. Okay? You recall from your basic thing something we're going to prove in the next line, and that is that xp minus px is almost zero. This is 10 to the minus 34th in joule seconds, right? Ridiculously small, okay? Well, and while you're at it, let's remember one of the first things that you learn from the Fourier analysis is that this momentum is written as a derivative, okay? So, given that p equal h bar k, we can go ahead and calculate this xp minus px, but it's got this tiny number in it, you see. So when I do this to a function, psi of x, some wave function, I don't care whether it's a solution or not, just any old function that's continuous and differentiable, I discover right here I 1 with a psi of x, so that cancels a lot, and leaves me with just the psi times h bar over I with a minus sign. Okay? So that's the proof that, the best proof I can give you really quickly, that the commutator is h bar I times the unit operator. Okay? So they only miss commuting by 0.0000033 zeros and then 1. Okay? So that is what I mean by they don't quite commute. So if you're doing classical mechanics, forget it. But if you're doing quantum mechanics where you're working with things whose action is down in the neighborhood of 1 h bar 10 to the minus 34 joules, then you really need this course, group theory in quantum mechanics. Okay? So that's where this oscillator business really shows. Now this is the ultimate quantum mechanical problem that we can solve because it has the highest symmetry that is available just for single closed non-coupled to the rest of the world quantum systems. So that's what we're going to study for just a few more slides here. So what we're going to do is we're going to take one of these factors, x plus ip, and I'm going to scale it just by energy, h bar omega, and we're going to call that the destruction operator. We're going to see why it's called that. Maybe that's not a good name since it implies something violent, but this is more wave-like kind of destruction. It's interfering type of destruction. And then the creation operator, seems it gives us another h bar of action, basically, in the problems that we'll be talking about, is the other factor, also divided by this one thing. Now, if you take up most of the modern quantum mechanics books, they'll carry these factors all the way through all of their derivations. That's really bad form. There's a good reason for defining these big X's and these big P's so that we don't have those factors bothering us in our algebra. We're going to have to write out the algebra in some detail. But we'll hold on to them for a while as we go through here and just look briefly at the commutation relation, not of X and P. We'll use that XP commutator equal h bar over I. But right now, let's just go ahead and work out what that comes out to be. So you can see why I don't want to keep those factors. Just writing this makes a very long expression here. You see I have here A, then A dagger, and then I have the A daggers first and the A second. It's really pretty annoying, okay? But when you cancel all those terms out, you get something rather simple. And these are the little px and the little p and the little x that are in the definitions here. Okay, so that comes out, you see, to be exactly 1. Okay, this commutator xp is h bar I1, as we've just proved before. Okay, so the commutation relations for these things is about as simple as it could be. And now it looks like, you know, there's not a 10 to the minus 34th in here anymore. This is just something that's going to be 1s and 2s and 3s, basically, in the matrix form. And its commutation relation is going to be the unit matrix. The trouble is it's going to be an infinite matrix, but we'll get to that. This is, after all, an infinite order group that we're making use of here. Okay, so remember that, or A dagger is equal to A dagger A plus 1. Okay, that's our everything we're going to build is just based on those relations and clever handling of them. Basically binomials that have to be treated. So the 1D harmonic oscillator in terms of A daggers is written this way. Remember when we factored it was x plus IP, x minus IP, and then the reverse. Okay, so that's a perfectly acceptable expression for the Hamiltonian. It's very obviously Hermitian. But I'm going to go ahead and use this one. Then it boils down to this. Okay. In other words, it boils down to A dagger A times H bar, and then half a quantum. That's what we're going to be calling 0-point energy. And this will be all the rest of the energy that we can actually work with. This is behind the scenes, can't be seen by ordinary mortals. Everything we can see is going to be located from coming there. Okay, now eigenstate creationism and destructionism, I guess. First of all, what we're going to look for is a ground state, eigenstate of this thing, with only that much energy, that h bar omega over 2. Okay? This is what we call the vacuum state. Okay, so we're going to ask for a state 0, no real quanta, that gives me exactly half. Okay, and there's the flip of it right there. So the idea is that the action on the ground state 0, or this is the ground ket, a dagger on the ground bra, is supposed to give nothing, 0 vectors. That's the way we can arrange to have this happen, you see. So I want to make sure that this A, when it hits a ket of this type, gives me nothing. But I got to be sure too that when I give it a bra, I try to hit it from the left, hoping I'll get something real. Okay, I get nothing because I hit that. Okay, so making those two our starting point, our nothing starting point, then we would have a situation where the expectation value of this thing would be what everyone knows about, 0 point energy, h bar omega over 2. But we need to go further than that. We need to find out what happens if you act with this thing, a dagger on the 0. We know that when we act with this thing on 0, we get nothing. But we got to get something by acting with this one. So, otherwise we don't have a theory at all. So, I'm going to call state number 1 a dagger times 0. Now you're getting an idea why I call, everyone else calls the a dagger a creation operator. Now, it's really a bad notation, because a dagger is like this, right, with a dagger, right? That isn't the way most people create, right? That sounds like a murderer, right? So the notation is kind of weird when you're trying to anthropomorphize all of this stuff. So, but just remember, the a dagger is the one that does the creation. I guess you could think of it as some sort of surgical tool that's going to create life out of a vacuum. Okay. Now, the Hamiltonian comes in, okay, with its h bar omega a dagger a plus the 0 point. Okay, so that's what we get when we apply the Hamiltonian to this number 1 state that we're going to be working with. And the question is, we're going to have to show that in fact the eigenvalue of h is just h bar omega plus this, and that's really what's going to happen as we go through the algebra here, you'll see. So I go ahead and I write a dagger as a dagger a plus 1, okay? And then we remember that a on this thing gives you 0, okay? I get this h bar omega over 2 dagger part just because that's what I started with. And I can then say, because that's 0, it's out of there, I end up with a thing that looks like this. Gives me h bar omega. The a dagger goes out to the 0 thing, and that's what we called state 1. And then there's a dagger times 0 again, again state 1. Okay, so now that's what I'm saying. E1 is going to be h omega plus E0. E0 being this half of a oscillator quanta. That's half of the energy, h bar omega, of an oscillator quanta. Single oscillator quanta. 1 meaning single. Well, that's kind of neat. That's the 1 quantum, or first excited eigenstate of this system that we've generated here. And the idea is we can keep doing this. It's not that trivial, though, because most of the time when you apply a creation operator's combination to other states, you don't just get a state that's normalized. This one happens to work out that way. We have some normalization to do, and that's always the bugbear of quantum mechanics. So we'll eventually have to do that. But as I say, this is the creation operator, whereas this would destroy that one, and as you can see here, it would give us back the state 0, and it works both ways. A dagger is a destruction operator when operating on bras from the other side. Okay, both of those give back vacuum ket or vacuum bra respectively. All right. So, what about this vacuum state, this coordinate representation of nothing? This wave function here, where the scalar product of a vacuum with a position x. And remember, we are talking about x's and p's here. Okay. So what I'm going to do is I can go ahead and write this thing back out again. A is x and p, x plus ip, times those factors we threw away for our work with the big x's and the big p's. Well, we bring them back at this point. That's a perfectly reasonable thing to do. And of course, I bring p back its representation in the x bra basis. Okay, so we end up with a differential equation. This is a Schrodinger equation, really, but Schrodinger didn't get them this way. This is a derivative of psi equals x times psi with a m omega over h bar, a coefficient. Okay? So I have to integrate this. This is d psi over x, well, I'm sorry, over psi, and let's see if there's anything I'm missing.
dx.
Yes, and then I'm going to integrate x dx. So there's the integral set up for that. And so I get a logarithm of psi and a logarithm of a constant. Okay, and then the integral of x dx is just x squared. So you solve that, and wow, that's cool. There's your Gaussian wave function. Right?
Why is it minus?
This minus right here.
You're bringing it to the other side.
Yeah.
Because
We made mistakes, I think.
is that?
We made mistake at the third line, and
Oh,
it has minus.
this
When
one
we-
right here.
Yeah.
Oh.
When we bring it on
Yes. I'll make a note of that. Yeah, that's right. This one right here, actually, though, we've got I here, and then the P is H bar over I.
No, when we put it other way, I mean, we have to put it on the right.
It's the first equation on the lower line that's off, right?
On this one.
Yeah.
Yes. Oh, yes. Right. That thing would then.
We put them on the other side of the.
That's right. Then I would get let's see, a positive thing. No.
Minus. We get
Yes.
minus when
You
we put
get
it
the
on
minus.
other side.
Yeah. On this one, right.
We have minus here, yeah.
Yeah. Okay. You're right. Bad me. I better remember to fix this one. Okay, so that's our deal, and you can see aside from making clumsy errors, this is a really fast way to get the vacuum wave function, right? It's pretty cool. Okay, and now it starts to be interesting because we're going to get this thing to give us the other wave functions as well, but also we're going to get all of the interrelations between them. Now, on the movie here, the simulation, this would be a picture just with this line right here that you'd see in an ordinary textbook. We're not an ordinary textbook. We've got what it really looks like there. And as you can see, there's a real and imaginary part. Okay, that's the real part with a dark blue, and then the light blue is the imaginary part. And there's the phasor coarse-grained to about 24 different boxes for the amplitude of this wave in this particular little potential. And there's your half of an h bar right there. And there's your h bar omega right there. This is half of it. So there's your 0-point energy. This thing sits just a little bit in energy, half a frequency off of the bottom of the potential well of the harmonica force. Okay? So that's now going at a frequency that is half of the frequency of the classical oscillator that this would be if it were a classical problem. And we're going to get to the point where we can make this into a classical problem. And that's called the coherent state. Okay? So that will come at the end. But let's keep going here. What I want to do is make sure that we get the right normalization. That's, as I say, the bugbear for that. That's not a difficult thing here to do if you do the Gaussian integral, which I won't bother to stop and do that. But the basic idea is that you get out of it a constant with a quarter power, a square root of a square root of pi h bar over m omega. So that's kind of strange looking thing. Now, the first excited state, we're going to create from this energy something, question mark. We already know that its energy is going to be right about there, but I'm indicating it as an unknown. And then once we get that, we should be able to destroy back to this. Okay, and that'll check our algebra in the thing. So the first excited wave function, psi1 x1, if everything we said before is right, would simply be this, x1 wave function, okay, is a dagger 0. So I go ahead and I stick the a dagger operator into this collection here, so I get an operator x0x, that's just x, and this is the derivative of x with the h bar over I, canceling that I. Okay, so I get a result here when the i's cancel. That's pretty simple. Okay, I get the Gaussian, and then minus just h bar times the derivative of the Gaussian. Okay, with that factor there, and then this factor there. Okay, so that comes down to this. It comes down to x plus I h bar m omega over h bar. I can get rid of that and get rid of that, so I have m omega x divided by the square root of m omega. That's just going to give me another one of these. So it just boils down to 2x, okay, times the Gaussian, okay, and then this thing here, the square root of m omega 2h bar, and then we had this, I think this is right here. I'm not sure if I skipped the thing here, but that looks, remember that, the 3/4 power now of x times the Gaussian. Okay? So, before we go any further, let's show it. And what I'm going to do over here, if I can, is, first of all, I'm going to kill the real destruction operator is right here. I'm simply going to zero this sucker. That means there's nothing going on in this well, okay? And of course, I can always make the ground state come up again, any size I want, but let's kill it. And let's just start the number 1 state by our counting. This one numbers from 1, 2, 3, 4. It should be numbering 0 if we're not using group theoretical notation. And there it is. And it's anti-symmetric, just like the first excited state of a square well is anti-symmetric, except this one is x times a Gaussian. That's kind of neat. But the normalization for this and all the others requires some algebra. So the really ugly part of this is about to come. We have to find a way to normal ordering, do normal ordering of these operators. And normal ordering, and this is where you can make a political analogy. The normal ordering is to have the destruction operators, the people that like war, on the right. They're the right wing, right? And the creators, the poets and people like us, right, are on the left. That's called normal ordering in quantum field theory. And anything has to do with creation and destruction operators. So
Creation is on the right?
the creation operators, we want to get this thing move the destructive A operators to the right of the creation operators. And the reason you want to do this is because you're going to be working with the vacuum kit with your big fat thing that you made. So if you can get everything, as much as possible, of this type on the right-hand side of your algebra, it's going to zero out.
For calculation.
Yes.
Easy calculation.
That's exactly right. We're going to be calculating matrix elements, including normalization. Okay? So that's where this gets tricky. This is the tricky part. Okay? We're going to have some function of A, some function of A dagger, and I don't want to start working on this thing right away. I want to see if I can get, and what I can do is I do a commutator between this function and this one. If I can pull that off, then just add this thing with the thing in reverse order. You see. So we're going to start with something like this, maybe. I want to get it to this form. Then this presumably is going to be simpler than this, and all ready to act on this. That's the idea, anyway. See how it works out here. Okay, so we're going to be having to evaluate a commutator of various powers of these. We'll just do the simple power, okay? So this is a generalization of the basic relation A dagger equal 1, commuted. All right? So let's look at some of those. A times A dagger squared, that turns out to be 2A dagger. Just write it out. You'll see this fairly quickly. I think this is a sort of an exercise to check this. Okay? And what's really cool, you see, is that this power law relationship is derivative-like. This is as though the destruction operator acting on the creation operator to some power gives me the derivative of that thing with respect to that power. Okay? As though I was taking a derivative of A dagger. I get 2A dagger. I get 3A dagger squared. I get that. Okay? So that's the first thing that we can find about commutators with A and A dagger. Now, commutator derivative relations are one thing, just the basic any operator, forget whether it's A's or A daggers. A commute with BC, that's AB with C on this side, and then, let's see if I've got that right, then A times BC, and then BC with A on the other side, okay? Now I can rewrite that as A commute BC plus the thing the other way. That's basically the operation that we're talking about up here, BAC, and then those cancel, so I'm left with this. And then if you look and see how this comes out, AC minus BAC and so forth, you get this. You get that the commutator of A with a product is the commutator A with the first factor, and then the C left out, and then B times the other commutator, and then now it's on the other side, A with C. So that's another derivative-like thing. So these things are behaving like derivatives, these commutator relations. And here's another example over here. A, B, C is turns inside out, so to speak, and AC with B, and then A with B, C. So those are, we're going to make use of those, a couple of things. Now, here is what we really need. We need to deal with the effect of a destruction operator on a creation operator that is to some power n. Now, the first one isn't so hard, A dagger n minus 1, okay? I just simply write out this commutator. So the other term is something in normal order. There's the destruction on the right. So I bring 0 Kepler on there. This is gone. Okay? Let's do A squared. Okay? That's the next step. I told you this gets a little hairy, but it's basically high school algebra with A's and A daggers. So I run this A squared here, and I already have the, let's see if that's right, I already have the A dagger A to the N to the A. So what I can do is, and that's just, I have to remember what I
We
did.
use the top line. No, the first line in that. No, the first line in this section.
in this set.
Yes, the first
Yeah,
line. We
this-
use that.
Yeah, that's right.
Just I2 is II, AA. Sorry,
Yeah,
A2 is AA.
Right.
A dagger N comes from the
Yes.
first line.
That's this, and then we've got another one. We're using this product relation right here to get that. That ends up with two of these, and basically comes out to be a binomial with a middle factor like that. And anyway, doing this over and over again, keep pushing this, we finally end up with an expression for, after you've done it 3 times, you can see that the binomial coefficients are showing up here with a factor, n factorial, n minus 3 factorial, n minus 2 factorial, n minus 1 factorial, and finally no n's at all. So this is kind of the way I like to do these A dagger A things, is to get them in terms of binomial coefficients. In this case, 3, 0 is just a 1, but 3, 1 here is 3, 3, 2 is 3, and then 3, 3 is 1. Those are the 3 binomial coefficients that come in this one. Okay. So the idea is that this can be generalized to this. This is an inductive proof of this relation, which we will need a very special case of this, where these two are equal, but there are other cases where we'll have them unequal, and calculating matrix elements and things like that later on for some group theoretical stuff. So here, this is a case where you take it from the abnormal ordering, with the creation operators totally on the right, to normal ordering, where the destruction operators are now on the right, where they belong. And this expression right here would do that for you. So we're going to use that to calculate the normalization. So the idea is that there is a normalization constant of some kind. It's not simple. We just worked out the algebra to make it. And we want to derive the normalization for the nth state obtained by the nth power of A dagger, the creation operator. That's this fellow right here. So the idea is that when I get done, I want this Ket-Bra scalar product to give me 1. And that means I want this A dagger N matrix element to be canceling this constant. So this constant has to be equal to the square root of whatever I get from that. And there's our expansion that we gave before in the special case. And so I'm going to be writing out the various terms of this, but since we're dealing with a vacuum, and that's where we start with every one of our creations expressions, everything from here on out is going to give me nothing. That's the idea of having the destructor on the right. And so there's your answer right there. The normalization constant is the square root of n factorial. I simply need to put the square root of n factorial here. Now go back and think about state number 1 or state number 0. 0 factorial is 1. 1 factorial is 1. 2 factorial, we didn't discuss that yet. There's 2. Right? So then you need a square root of 2, and so forth. Okay? So we were lucky. We could avoid this stuff for the first few states. But you can't avoid it for the, shall we say, the third state, and we'll be getting those shortly here. So this is root factorial normalization of this oscillator. Now we can go and make higher states with this thing. That is, we can go and do an A to the n plus 1. We can apply a destruction operator, do an A dagger of this quantum state. And there's where we're going to get all of our matrix elements for the A operators. You see what I did here was I said, oh boy, that's almost a state with an n plus 1. All I need is a square root of n plus 1 down here, so I'll just multiply by the square root of n plus 1. Then I've got it. That's a state n plus 1 right there, if this is a state for n. It's supposed to be true for all n that are positive, including n equals 0, which most mathematicians would say is positive. Okay, so once again, I'm making use of one of the first relations up there to get this thing into normal order. So there it is in normal order. Okay, I lost a power there. Okay, this I can throw away because it's operating on the vacuum. Okay, so I'm just left with this, and then this n factorial has an n in it, so I get a square root of n here, and then n minus 1 factor. That's exactly the state with one less quanta, normalized correctly. So there's the destruction operator's effect on n. It's to give you a factor, square root of n, and then a state with one less. The creator is giving you a factor n plus 1, and then a state that's one greater. And Feynman's mnemonic that he mentions in volume 3 of his 3-volume series, which, by the way, if I haven't advertised it yet, I advertise it again. Worth reading, all 3. Okay, every physicist should do that. Anyway, his mnemonic rule is whatever you put in a radical, the larger of the two quantum. In other words, you're greedy, you want quantum. Okay, so if I see an n plus 1 anywhere here that's bigger than n, I put n plus 1. If I look here, that's the smaller, that's the larger, that's the one I put. That's a mnemonic, okay? Just, because you're going to be doing this, quite a bit if you have to calculate tensorial matrix elements and things like that, like we're going to do later on. Anyway, here's what the matrices actually look like. And this matrix goes forever. This is an infinite matrix. I should do this in some funny color to indicate that it just doesn't stop on this side. And neither does this. But what's weird about it, and this is something that I mentioned we were doing inverses, okay? All of the matrices that we've studied so far are finite, and if they're matrices whose dagger is the inverse, you almost always assume that if you can get a matrix inverse that multiplied by the matrix gives you 1, that's called getting an inverse, you're guaranteed you don't have to do any more work in order to get the reverse, that m in the inverse is also equal to 1. Not so with infinite matrices. And this is a counter example to any theorem that would say you can always do that. You can't do it for infinite matrices because these are different. Okay, these are not equal. The commutation relation is with an n equal 1 here, not 0. Okay, so welcome to infinite dimensional quantum space. And this is something that goes with that territory. All right, now that we've got a root factorial normalization, we can go ahead and apply creation operators to build the states that are next. Let's go, I think I have a few examples here. But before we do that, the number operator, this thing, A dagger A, okay, operating on n, okay? So I do A dagger A on this state, right here, okay? So I take my A dagger A, put it there, okay? And then write that out in normal order, okay? A dagger n and A dagger n minus 1 with, and there it is in normal order. I can throw that away because it's operating on the vacuum, okay? So I'm just left with that. And that's that, okay? I've got an n over n factorial right here. Okay? I need that thing right there, and I need that too. So, what this operator does is count quanta. That's cool. Okay? Now, that's part of our Hamiltonian, right? The only thing that we left out here is 0 point. There's a 0 point. Okay? Our Hamiltonian was h bar omega a dagger a plus half an oscillator quanta times the unit operator. So those are our eigenvalues, and that's why I draw all those states up by a half from the bottom of the classical oscillator. Okay, so there's a matrix view of what this would look like if I drew the first 5 or 6 dimensions of this oscillator. H bar, and we call big N number operator sometimes. I don't use that notation very much. And then the 0 point operator is the unit matrix times a half, everything multiplied by h bar omega. Okay, expectation values. This is important. I'm going to breeze through it again, but the idea is if you want an expectation value of x, all you need is this factor times a plus a dagger over 2. And if you want momentum, it's sort of an inverse factor, inverse with the m omega. M omega is the denominator on this one, times momentum. And that's a minus a dagger over 2i. So this is like cosine and sine, if a and a dagger are exponentials. Okay, and they are. That's what they are, really, as we'll see soon enough here. So the expectation value for position, the x bar in quantum state n, that's sometimes the way they write it, but that's a better way. It's Dirac-like. Okay? Well, I'm going to be taking this x factor here with the m omega over 2h. I can write that thing upside down, h bar over 2m omega a plus a dagger. Okay? So the expectation value for this one comes out to be 0. This a dagger would hit the n, make it n plus 1. That, with this, they're orthogonal. This is a operating on that, same thing. That gives 0. Okay? So the expectation value for position for an oscillator like that in any state, 0. There's just as much probability on either side of the origin. And the momentum is the same way. But expectation value of the square, not 0. This is not 0. Okay, so that needs to be worked out. And this is an expansion that does it. There's a commutation relation to solve that expansion. And you get that the expectation for that is twice the quanta plus 1. In both cases, but with different factors. Okay, this one has m omega upstairs, this one has it downstairs. Okay, uncertainty, that really means the product of these things. When we product the delta p and the delta x, but that's what the delta x and delta p look like. Okay, this is the uncertainty. A product actually stated completely. It's not that ugly at all. It's this. So this is the uncertainty product for arbitrary quantum number. But the one that you're used to, is the one for the 0 quanta. And this is about as good as it gets, h bar over 2. That's the 0 point effect right there coming in. Okay, this is called minimum uncertainty product occurs for the 0 quantum eigenstate, the bottom. And then it just grows as we go up. Now here's, we pause for, I call, sobering considerations of the quantum world versus the classical one. Consider a high quantum state, say 20. Okay, that's more than I can really safely do with a program set the way it is. I need to make it finer to go up 20. I can go up probably 10 here without killing too much, so let's go ahead and do that. I'll kill this thing. I'll go up here about 10 or 12, and you can see it's really zipping, but I can see I've got a problem already because this is all wrapped around a circle. If I've got a lot of probability in the ends, that's not quite right. This is a better representation of the way that you get with finer graining. Okay, so I'll zero that. But we didn't get to show the two quanta. I might as well show that one while we're at it. Okay. But look at this one. This is kind of neat. If you fit this envelope, it fits an arc cosine. That's a classical effect. If I have something that's oscillating from here to here, like my hand, you can see your eye catches my hand here and it catches it here, right? Because it's very high probability as it's turning around, it's going to stand there for a while. It's going fast here and then it stands here. So these things are always higher. A classical Newton person would rationalize. Therefore, we should expect high amplitudes and the ends and low in the middle. And in fact, it fits perfectly the arc cosine. That's a plot of an arc cosine. I think that's pretty neat. Okay. Anyway, the n equal 20 wave is a long way from classical. Classical is 1 joule. Okay. For a 1 Hertz oscillator, that's pretty slow. 1 joule would take a quantum number of roughly 10 to 34, really 35, right? You got a computer that can handle that kind of number? Forget it, right? Not for a long time. Not until we start building quantum analog computers can we play games of that magnitude. And that's starting to happen, so I am optimistic. All right, beat dynamics. We want to go through this fairly quickly because I want to get to the coherent state, which is the ultimate beat dynamics. But this is something that would happen for any closed well. Square well, we talked a little bit about this. What happens when you mix two different states? Okay, well, it oscillates. It oscillates with the beat frequency. I'm just going to mix the state consisting of vacuum and first excited. Okay, that's all we're going to mix here. All right, and I'll mix it with some apportionment. Psi 0 is the amplitude of the vacuum state. Psi 1 is the amplitude of the excited state. Now, presumably, we'll normalize the thing so that the sum of the squares, absolute squares, of these two apportionments here, these amplitudes, would add up to 1. Okay, that would mean we have one, I don't want to even say the word, particle, okay, in this system. We're talking about, if we're talking about electromagnetism, we mean we'd have one photon, okay, in the system. But we're capable of having 100 photons, 1,000 photons, 1 million photons, right, in a quantum field theory, right? Just for a single mode, we've got that, okay? So, you know, particles are kind of passé, I would say, as we begin these discussions and carry them to some level. But still, we can think of a classical oscillator, some sort of nano oscillator that would be described by a wave function like that. That's interesting to do, and that's why I want to show this is the simplest case where I just take it a little bit out of the ground state. So I have a large number here and maybe a smaller number, much smaller number for the amplitude psi 1. Okay? So that's going to be our wave function. It's not an eigenstate. It's a combination of eigenstates. And that's the way you get motion in any of the Schrodinger-like quantum systems, is you take eigenstates and have at least two to tango. You don't tango if you only have one, because only the phase is wiggling and you can't see that. But we can see the probability moving with this combination. So we're going to be asking what is the amplitude, or more to the point, amplitude squared. This is the absolute value, and this would be the probability. So the square root of this is what we're going to be looking at as an amplitude, modulo amplitude of this wave. And as you can see, its binomial comes out with a nice cosine of this minus that. And the idea is, of course, that the 0 point energy is not to be seen anywhere here, but omega 1 minus omega 0 is to be seen there. And omega 0 isn't quite 0, in fact. It's a half. And this is 1 times h bar omega. So what we're going to see is this thing slashing back and forth. Let's turn over to this thing and start the ground state. So I'll start the ground state. That's something you can't turn off in a real system. This one's really cool. I can literally kill the vacuum, but you can't kill a real vacuum. It's already dead, as dead it's going to be. So I start with this, and then I add, you see, it is not moving. You're not allowed to see the man behind the curtain inside there, right? In real world quantum mechanics, okay? You can't see that heartbeat, all right? Now, if this was an oscillator of mass m, that would be mc squared. Just remember that. But we usually take our origin to be right here and throw away the mc squared, right? In this case, you get a half omega h bar, okay, for that. All right, now let's just add a little tiny bit of this. It's moving, right? I added such a small amount, such a tiny amount. You can see very clearly that it's vibrating back and forth at exactly the frequency between these two levels. The absolute frequency means nothing in quantum mechanics. Only the difference means something. And there's your difference right there, modulated by this tiny number that involves the difference between these. You see, I have a psi 0 squared here, which is large, a small amount of psi 1, and then a product right here. And in order for this thing to amount to anything, there has to be an overlap between psi 0 and psi 1 at some points x. And this has lots of overlap. So no problem getting an oscillation going here. Now, if I crank up the amplitude right here, and this is, say, and you can see the thing moving there, now I get a very good oscillation. And if I make it about equal, which is we call saturation of the oscillator state, say about there, back and forth it goes. It's sort of a complicated motion. It basically amounts to one part of the one showing very strongly and then the other part of it. But that's the way it would work with a square well. The first two states of square well aren't too different from this. It's just that they're not made of such pure Gaussians as the excited state, which is x times the Gaussian, and the ground state, which is the Gaussian. So this is rather special in that sense. Okay? So there's your vibration. Now, the point is that any two states on here will oscillate at frequency omega. That's the only thing we've got going here. you see. And now this one would oscillate at 2 omega. If I decided at the next state there, and that means I'm going to have to kill everything, start the ground state again, heat up the vacuum, and then start the number 2, n equal 2, that's number 3 on our way of looking at the thing, and give it, you know, 50-50, then I'm going to see that oscillate. But that oscillation is now, because I picked it way up here, it is twice the frequency of omega. So anything you do with 2 things on here is going to be some multiple of h bar of omega, at frequency. And this is the other thing that's true, is no matter how many players I take in this orchestra, whatever sort of chaotic mess I get, it's always got to return after 1 revolution of this, which is the period inverse 2 pi over omega. Okay? So start that, and then wait. They're halfway, and then finally we're going to be all the way. I should have every one of those back where it started at the time I said mark. Now that's something you can play around with this and see and make, you know, interesting cases where that happens. But we've got other fish here to fry, so we're going to go on from this. So here's where you get the idea of a phasor for quantum oscillator. Okay, make a combination state, and then it will have a simple phasor with a frequency of omega. And this program is capable of showing that, but I won't bother with that right now. We've got, as I say, other things to do. So listen here, beat frequency is eigenfrequency difference, and that's what you're going to see. Beat frequency omega is a transition frequency. If I shine some sort of stimulus into this system, say it's a molecular vibration in first the vacuum state, but then I shine in some frequency h bar, the first thing that's going to get excited is going to be that. So we're going to make the thing oscillate its charge, you see, and it will be pi over 2 behind my field for a while until it builds up, and then it'll reverse. You see, it'll become the donor and start radiating light back out. Now, none of that is in this program. That's taking us a much bigger step as far as simulating a quantum state. Remember, that's the thing about Schrodinger mechanics, is it's isolated, right? Or very nearly isolated. It's, the outside world is small perturbations, or you get a big mess because of all of the oscillators that are waiting outside to get tangling with this thing. So the transition frequency is the transition energy divided by h bar, which is a good lesson. And omega is the frequency of a radiating antenna of a transmitter or a receiver. That thing can be either a transmitter or a receiver. That means it can be either an emitter or an absorber. And usually it's a dipole symmetry. That's the thing that gives you the biggest range, is the dipole oscillator. Quadrupoles, much weaker as far as getting information and radiation out. But they're there waiting to participate if you could find some way to read them, like Raman scattering, for example. Okay, coherent states. This is the cool stuff. This is cool. But also lessons about how do you translate, how do you take a wave function and shove it to some distance a away from where it was before. Say that a wave function that was centered around the origin, like our ground state, and I just shove it, I just push it over and let it go from a position that's located out a ways from the origin by distance a. Well, we're going to make a translation operator that does that. Okay? The other possibility, instead of shoving this, is what would normally happen if you were to just put a nice mass with a string or a ball. It's on some sort of pendulum thing, and let kids come in. First thing they do is give it a kick, right? The adults would be more like take it off center by a shove and let it go, right? That's what this will do. But with this operator that we're going to build here, it's got to give some momentum to it, an impulse. Okay? So what we want to do, since we can write these wave functions either in momentum space or in position space, I can do a thing that's entirely a function of momentum. Will look just like what we've already done here, algebraically. Somewhat different, actually, but that's the sort of equation that I would be doing. So I would be coming in here with this boost of some amount of momentum and applying it and getting a wave function that is shifted by that amount. Okay? So, as I say, this one shifts the state x space, a units left. Okay? Now, you have to be a little careful here. This is kind of strange because actually what I would be, if I were to write a psi of x minus a, that would mean a wave function that was pushed to the right. This particular one, I'm imagining that I am literally going to take something that is at x and I'm going to move it to the left. That is, I'm going to move it to x minus a. So you have to, this is that duality that I've talked about before, okay? We've got a frame that's the laboratory, and we've got a frame associated with the wave that's riding in the laboratory, okay? And if this is the wave and this is the laboratory, this thing means I'm going to go to the left, okay, a units. Now that means if you flip this thing around, okay, that means that this T dagger A x equal x minus a, that would be equivalent to T undaggered, x daggered, you see, and x minus a turns into a bra when you dagger it. So there's the bra x minus a, and there's the operator TA on the x. Now you see where this comes up is here's the TA, here's the psi, right? This TA is designed to take the psi to the right. The way it does is that it takes the bra to the left, so that it looks like the psi went right by A. That's our Archimedes principle, our Mach principle, right? Momentum plays the same game. Momentum plays the same game. This is explained terribly in all the comic books I know, because they want to, you know, grab the bull by the horns, and that means grab the duality by the horns, so you know there's a relativity at work here. This has the same thing here. Now when we get to the bottom of this, we'll do this with a plane wave, and you can check yourself that all of this arithmetic comes. So let's do the translation operators in a geometric way. This tiny translation, A going from A to dA, or from 0 to dA, is the identity operator plus some generator times dA. Okay? Now what's the generator? The generator is just a derivative of the operator evaluated near the identity, the origin. If we're thinking of this as a group operator, fine. This is what Lie had in mind when he did Lie groups. So I'm going to be making a generator of translations and also a generator of boosts, okay, as we go through this. Okay? Now to be able to 1 plus this. Now the idea is to apply this thing many times to get a finite. So I take this thing that's divided the distance I want to go into n little steps. And I take the limit as n goes to infinity, because I want to be very precise, of this little boost, this nano boost here. I take this nano boost to the billionth power, okay, and I end up with a boost. Actually, translation in this case, a boost in this case. All right? In other words, I end up with an exponential times this generator. That's Lie group elementary theory. That's what's going on when you do that. Okay? So if I do a translation of a wave function psi of x, I need to take an exponential of the thing. That's e to the minus a derivative with respect to x. And there's a psi of x. Okay? Now, that comes out to be a series, which, if things work out well, will converge for us, and give us, at least on a computer, you'll be able to work that out as an answer. This is the same thing. Same idea, but now we're working with the p operator. Now, what turns out is g relates to momentum. You see this g is a partial with respect to the coordinate change that we want to make. Okay, and just on the other, this thing relates to position. You see, this position operator in momentum space looks like that. That's the symmetry that you learned from the oscillator being easily able to work in both sides of phase space. So what we usually do is we put the IH bar on this momentum here. That means we have a minus partial with respect to x for our generator. And the k here, I do an I over hx to get the minus 1 over h bar partial with respect to the k. That would be the wave vector or wave number. Okay. So what we're going to end up with here, you see, is a translation operator that involves momentum, and a boost operator, something that's going to change momentum, is going to involve position in the exponent. A plus a dagger for this one, a dagger minus a for the translation. Now, we want to check this on a plane wave with p equal h bar k. Okay, this is going to be our wave function. And we're going to see if this translation, you see, working on this thing right here, is going to give us what we say it's going to give us. And that would be a function of x minus a. So you apply this thing to this. Well, this thing is an eigenstate of the momentum operator, so I get an e to the minus I a k I k x. That gives me e to the I k x minus a, exactly what I want. So you get confused by these operators and find a wave function that you can look at and see how it works. This one is really easy to calculate. So is this one. On a plane wave, I want to have the momentum here, this thing. I want it to boost that momentum with a plus sign. And indeed, that's what I get. E to the I bx, you see. Now this thing right here has a positive sign. This thing here has a negative sign. But that's what the doctor ordered, because I want this one to go positive. If I'm going to, boost it positively. So I'm going to add to k here. I'm going to subtract from x here in order to translate positively. That's the story of the boost and the translation. Now we're going to make use of them. And the question is, what do you do here? Which should come first? If I want to do both translation, I want to be out here. I also want to kick it a little bit. Which should I do first? Which should come first? Well, this is kind of analogous to the Euler versus Darboux thing that we ran into before. See, here's a translation operator, the minus I a momentum, and this is the boost, e to the I b x. It's going to add to the k, so we're going to subtract from the x in order to translate to the positive side. All right? The answer is neither or both. We do a combined boost translation operator in general. And then we can go anywhere in phase space. Now this is like e to the I Darboux vector omega x
omega y, omega z, whatever, times the various sigma or angular momentum operators, right? This is more like Darboux. I'm doing it all together. The combination of this thing, this product, that's more like Euler, e to the I jz, then e to the I jy times beta, and then e to the I jz times gamma. Separate factors. You can't add the exponents because they don't commute. Unless h bar can be taken to be 0.
You just have 2 dimension here. 6 dimension.
Well, that is exactly right, because if you were talking about a full x, y, and z, then your phase space is 6-dimensional. Your coordinate space, only 3. And that's what we were dealing with before. We didn't treat the momentum as part of a phase space, although later we have to do that. We will do that. So this was the Darboux rotation, that was the Euler. Just to get this in context, because we're going to come back to that. Now the way the most quantum mechanics books handles this is with something called the Baker-Campbell-Hausdorff identity. And that's, once you've done all the algebra they've done, which involves stuff we've already talked about a little bit here, it's okay. I think we can do better, but this will do for now if I'm going to evaluate a thing like that, okay? Well, what I can do with this theorem is I can say e to the I a plus b is almost the same as e to the I, or e to the a, e to the b product. You just have to subtract the commutator. And a whole lot more if the commutator doesn't commute with a and b. If the commutator commutes with a and b, and that's what's true for most of our angular operators, is we don't have to go any further than this. Otherwise, there's a whole series of things that you have to do here. So you see, exponentiation of operators in an algebraic and closed form is a pretty tricky business, unless the commutator commutes with the factors. Okay, now I say left as exercise. This was a whole career for these people, so it's just not an easy exercise at all. But in any case, that's what we use here to rewrite this combined operator as a factor x and a factor. Otherwise, we could just do this and forget this little thing here. But I prefer to do this simply because it's a more complete treatment of what we do here. So you have a choice. You can put the boost operator after the translation operator, and then you put a minus IAB, or you can write the boost operator first, and this one comes second, and put a plus. That's the result of the Baker-Campbell idea. So reordering only affects the overall phase, but the phase is important. So we have to do all of this sort of operation. Okay, so let's look at this. This would be A dagger plus A multiplied by the boost parameter and the translation parameter A times A dagger minus A. That's the momentum, that's the position right there. Appropriately scaled. And what we're going to do is we're going to give write this out in terms of A dagger and A, okay, which can be written this way or this way. You can put these in either form. You're going to have a dying exponential of this alpha factor. Now, what is this alpha factor? That's the thing that's cool. The complex phasor coordinate that we're going to get to describe boosting and translating states has both a real part and an imaginary part. The real part is the actual position that the thing has been moved, and the imaginary part, you guess it, this is a quantum phasor. Real part this way, imaginary part this way. Those are the two parameters of this alpha. This is a complex number that describes your position in phase space. Okay. Okay. So TC has just told me we've got to hurry this up, so I'm going to just show the results here. It's rather nice.
coherent wave packet state is just an e to the alpha creation operator. The destruction operator has been put to the right and is killed by the vacuum, so you get something like this, which is easy to calculate. It's just a power series. And we're going to show the time evolution of this thing on the screen over there. And this is actually set up already. I assumed we were going to have to rush a little bit at the end. But this is the actual details of the motion you're about to see over there, where the position and the momentum are described essentially by classical variables, sines and cosines of the frequency. So I'm going to go ahead now and I'm going to run that state in space-time. So you can see it actually oscillating around the center of that potential, which will disappear behind the plot because we're plotting time upwards. But what I've done is I have translated, not boosted, the ground state. So I'm starting with a full amplitude, and that's what it's going to do. The initial conditions for a harmonic oscillator with an initial position but no initial velocity would be that. When you turn your head on the side, that's a cosine. And it will follow that forever. Is it perfectly, and because all of the frequencies here are multiples of h bar, it doesn't matter how many states I have to sum up in an expression like we just derived in order to make a state that looks like that.